All right, we're going to look today at section 4.3, and this is arithmetic in our system. Hindu-Arabic system is our number system. So we're going to take a look at how we do arithmetic in a few different ways. So the first thing I want to look at is what expanded form is. So expanded form is a form in which the value of digits in each position is made clear. So instead of thinking as 942 as an all-together number, you think of it as 9 hundreds plus 4 tens plus 2 ones. Okay, so when we do this, though, we often end up writing it like this. It's 9 times 100 plus 4 times 10, and then 2 times the number 1. And we talked last time about how these other systems, like the Mayans and the Babylonians, had these powers of 20 and powers of 60 showing up in their numbers. And I mentioned, we didn't go too much into depth, but I did mention the fact that our system does that too. So we have a base 10 system because we have the 10 fingers, right? But all of these numbers are powers of 10. And so the number 100 is actually 9 times, well, not 9, but the number 100 is actually 10 squared. The number 10 is actually 10 to the first. And the number 1 is actually 10 to the 0. So one of the ways that you can quickly remember what the power is that the power is based, well, it's not based on, but it's the same as the number of zeros that are present. So you see in the number 100, you have 2 zeros, so it's 10 to the 0, 10 to the 2, okay? In the number 1, you have 0 zeros, so it's 10 to the 0. So that's a quick remembrance of how you can go with these different place values. So we're going to take a look at a couple of examples, one going into expanded form and one pulling expanded form back into our standard form. So we have the number 12,398, and we're going to write it in expanded form. If you can go straight there to the powers of 10, that's great. I'm just going to do an in-between step for those who might want to see that. The number 1 is in the thousands, the 10,000s place. So it's 1 10,000. The number 2 is in the thousands place. The number 3 is in the hundreds place. 9 is in the tens place. And 8 is in the ones place. So this is a form of the expanded form. But there's going to be places where they're going to want you to write it with powers of 10 as well. So I want to show you both. So if we're writing this with the powers of 10, we're going to have 1 times 10 to what power? It's 4. Why is it 4? Yeah, there's 4 zeros, exactly. Or at least we can say that that's a way to check. And then I've got 2 times 10 to what? The third. 3 times 10 to the second. 9 times 10 to the first. And 8 times 10 to the 0. Now, if we're going from an expanded form back into our form, as long as the powers of 10 are not skipped, right? So look at this. This says 10 to the 5th, 10 to the 4th, 10 to the 3rd, 10 squared, 10 to the 1st, 10 to the 0. So as long as there's not any skipping going on, then the numbers are just showing up in order of what they would show up at. So they're all present from 5 down to 0. So we can literally write the numbers that come in front of the time, the multiplication part, as the digit in that place value. So we have 5, and then 0, and then 3, and then 5, and then 6, and then 8. Now, if there was something that was skipped, if we didn't see something present, we need to be a little bit more careful so that we would represent something, wouldn't represent something that's skipping along the way. But we're just taking a look at these numbers right here. We get 503,608. Okay, is that all right? So what we're going to do next is we're going to actually add and subtract in expanded form. And You can kind of shortcut this system, but you need to be a little bit careful because you might make a mistake as you do it. So we're going to actually do it out the long way we're sort of supposed to be doing it. And in order to do that, we need the distributive property. So I'm writing down the distributive property sort of backwards of the way that you might have thought about it in the past. If you have an B times A and C times A, that's the same, and they're added. It's the same as having B plus C times A. And normally we kind of look at it from this perspective and we go back to the left-hand side and we say, oh, look, I can just distribute the A across the equal sign or across the parentheses. That's fine. But this is sort of a pulling it out because I noticed that they both have something in common. Okay? So it works for all real numbers A, B, and C. And we're going to be using it for expanded form. So I'll show you where it presents itself when we get there. Okay, so we have two-digit numbers. They're not anything very exciting. They're kind of small numbers. You can do this with bigger numbers as well. But what we're going to do is we're going to be writing the 75 and the 34 in expanded form. So 75 would be 7. Actually, I'll write it over here. 7 times 10 to the 1, because it's in the tens place. And 5 times 10 to the 0. And then 34 lines up underneath because it's 3 times 10 to the 1 and 4 times 10 to the 0. Everybody good so far? Okay, so we're going to add it like this. We did this, well, we did an example of this last time when we were working with the Egyptians and we were doing their addition and subtraction, right, where we did it vertically like this. And we do need to work, well, I shouldn't even say that. We can work from left to right or right to left. It doesn't really matter. There's going to be an additional step in a moment that's going to matter a little bit. So let's just work from left to right because we can. So if I add the column down, 7 plus 3 would be 10. So this is 10 times 10 to the first. And then 5 and 4 would be 9, which is 9 times 10 to the 0. So here's what happens. What happens is that I ended up with a two-digit number 10 times a 10. It's not a one-digit number, right? So we have to break that apart. This ends up being 1 times 10 squared. And then I have 0 times 10 to the first. And I'll show you where I got those individual pieces from. Let me write this thing down. So this number right here, 1, is now 1 place value bigger. So it's not times 10 to the first anymore, it's times 10 to the 0. Okay, it's a 1 place value bigger. Whereas this 0 shows up right here. So the 1 is coming out over here, the 0 is showing up right there. And now I've got them all written down in order, 10 squared, 10 to the first, and then 10 to the 0. And my total then at the end would be 109 because those are the coefficients present for each of the powers of 10. Okay? This is the distributive property in reverse. The reason that I'm able to add the 4 and the 9 here together is because they're both times the same power of 10. Now, you do it all the time. You don't even think about it, right? If you add numbers together, you know you add the ones column together. You know you add everything in the tens column together. But that's the distributive property that's actually present when you're doing that. That's why that works, okay? Let's do subtraction. It's very similar. We're going to write down the same sort of thing. 7 times 10 to the first plus 4 times 10 to the 0. And it's minus 4 times 10 to the first. And it's minus 8 times 10 to the 0. So we're subtracting both of the values, both the number 40 and the number 8. Make sure to pay attention to that extra subtraction piece. Now the same problem happens here as happened when we were doing the Babylonians. In the right-hand column here, I have 4 minus 8, and I can't actually take 8 away from 4, right? So I have to do some regrouping. I take the number 7 here, and I borrow 1 from it, and I make it a 6. And in borrowing it, I add 10 more over here, because I really borrowed a 10, right? So now, in a very real sense, I have, and I'll write another step for it, but I have 6 times 10 to the 1 minus 14 times 10 to the 0 minus 4 times 10 to the 1 minus 8 times 10, that should be a plus, sorry, 10 to the 0. There's a plus right there for the 14. I got carried away. Plus right there, please. Okay, so once there's enough on the top number to take away the value on the bottom, again, we could work from left to right if you wish. You can work from right to left as well. But I can do 6 minus 4, that's 2, times 10 to the 1. Again, that's the distributive property in reverse. And then I can do 14 minus 8, and 14 minus 8 is 6. And then these coefficients in front form my 2-digit number. That's my answer. The answer is 26.
Why is there a minus sign on the last row?
You mean on the 8?
No, on the 6.
It shouldn't be, because I keep getting carried away with my minuses. Thank you, Savannah. I appreciate it. Yep, it should be a plus. Okay, anything else? Okay, have you heard of an abacus before? I'm not going to ask you what it is. I just want to know if you've heard of one. Some of you say yes, some of you say no. An abacus is a very old-fashioned calculator. That's what it really is. Okay, very old-fashioned, like pre-technology. One of the oldest methods for speed calculating. That's what I mean by calculator. It's got beads. There's beads that are above a rod in the middle, right? You see my rod in the middle? There's beads that are above this, and there's beads that are below. They've colored it very nicely for you. If you had the physical abacus, there would be no color differentiation on your beads. They'd just all be the same or all be various colors. They wouldn't have any meaning. They're coloring them nicely to try to show you that they have done something different with them. So the blue ones, the ones that are the ones that are pushed away from the vertical bar in the or the horizontal bar in the middle, and the black ones are the ones that are pushed toward it. And that's true from both the top of the abacus and the bottom of the abacus. Okay, so this is actually a physical object. This is just a picture representation of it. The beads that are pushed toward the middle rod are active beads. They count. The ones that are pushed away are ignored. Beads above the bar are worth 5. Beads below are worth 1. That doesn't actually say that, but they are. And the base 10 place value with the largest place is the value on the left. In other words, it goes in the same order that our numbers go in. Biggest value on the left, smallest value on the right. So it starts with 10 to the 0 on the far right. You see it listed below. And they go in powers of 10 as you go to the left. So the biggest one, this one is 10 to the 4th, right? And here's how we count the beads. We're just going to go from left to right because it doesn't make any difference. But on this first rod on the left-hand side, there's 3 active beads because they're the beads that are pushed toward the metal rod in the middle. Okay, the beads below are worth 1, so this is the number 3. On the next rod, there's only 1 bead that's pushed toward the rod in the middle. It's worth 1, so this is the number 1. The third rod is the first time where we see a bead from above and below pushed. The one from above is worth 5. The ones from below are worth 1 each. So that would be a 7. On this rod, right, the 10 to the 1 rod, there's nothing pushed toward the middle. So that means it's the number 0. And on the last rod, we have 1 bead above pushed, 1 bead below pushed. So it's 5 from above, 1 from below. We get the number 6. This is the abacus's representation of the number 31,706. That's what it is. Okay, are you okay? right, we're going to do a couple of examples, both going from our number into what the drawing would look like and the other way around. So this picture, you'll have to draw in because I can't get it to draw in very nicely for you either. You don't need to worry about changing colors on the rods. None of that's really important. It's just a visual to help out. What does matter is the placement. Is the bead pushed away from the middle rod or is it pushed toward the middle rod? So I'm going to give you a second to go ahead and draw that out first with your beads in the right locations.
What's the point of the other beads being there?
Yeah, so that's a good question. Remember, this is a physical object. So the beads are on the rods and the beads don't come off. So there's a physical bead, like an actual bead above that middle rod, the horizontal rod that's going on there. So I can't take it off of that rod that it's sliding along. The best I can do is to push it away or push it toward the middle, but the beads don't come off. If we were just drawing a picture, there'd be no reason to draw them. I mean, like, that's not it, but it's an actual physical object, right? Like, I could bring in a wooden abacus and we could actually see that it looks like this and the beads are going to be 4 beads below, 1 bead above, and it looks like that. Okay, you ready to do number 5? What number is present? We're just going to go from left to right. What number is present on the first rod of number 5? It's the number 1. There's only 1 bead that's pushed toward the middle, and it's a bead from below. What's the number on the second rod? 0. There are no beads pushed toward the middle. Third rod. There's a 2. 2 of them from below are pushed to the middle. Fourth rod. 5. Okay, the one from above is pushed down. That's why they're coloring them for you, is because it's kind of hard to see the difference sometimes. But the one from above is pushed down, so it's worth 5. And how about the last one? It's a 6. One from above, one from below. So this number is 10,256. Okay, so in my math lab, you're not going to be able to do number 6 the way we're doing it on paper because they're not going to have a way for you to actually draw it. It would be a multiple choice type question if you were asked this way, right? But we are going to draw it together. So you're going to draw, to start with, an abacus. And it's going to have a middle rod like this. And it's going to have 5 rods. So you've got 1 here, 2, 3, 4, and 5. And you have to have 5 beads on every rod, 1 above and the 4 below. There's going to be 5 beads there that you're going to draw. I'm not going to draw mine in different colors. I'm going to make them all, let's go with a yellow, a pale yellow. Well, dark yellow, we'll do dark yellow. So all my beads are going to be yellow. Our first number is the number 7. How do I get a 7 if this is my representation? Yep, 1 on top. And 2 on bottom. All right, that's good enough. But that's only 3 beads, and I need 5 beads on my rod. I need 2 more beads, and where will they be? They'll be pushed to the bottom. So on the bottom of this, I have 2 more beads. Does that make sense? Great. The next number is 0. How do I get a 0 with this representation? 4 on the bottom, and they're pushed all the way to the bottom, right? Yep. So there's 4 pushed all the way to the bottom. And 1 at the very top. So everything, there's 5 beads, but everything is pushed away from the middle line. The number 1, how do I get that? Okay, 1 underneath this bar on the bottom, and then 3 more underneath that. That's what I'm hearing you saying. That's right. And then 1 pushed to the very top, right? Okay, ready? Good? Doing good? Okay, 6. How do I get a 6? Yep. I need one from the top and from the bottom pushed to the middle. So here's one on the top. Good grief. Here's one on the bottom. And then what? 3 more pushed down, right? There's always 4 on bottom. There's always 1 bead on top. And the last number is a 3. How do I get 3? 3 of the bottom ones pushed to the middle. What else do I need? 1 at the very top and 1 at the very bottom. Okay, everybody good for that? We have one more thing to do in this section. This is the shorter of the 2 sections for today. All right. We're going to do something called lattice multiplication, or the lattice method for products. So this is sort of an itemized description of how to do this, and then we'll do it together and you can see how it works. We're going to create rows and columns for our digits, divide the boxes along the diagonals, compute each single digit product with the tens digit on the top left, ones digit on the bottom right, and we're going to add along the diagonals from right to left. So take a minute and write those down. All right, those of you who are my education majors, you'll see this again if you haven't already taken number theory. This is currently used in a lot of curriculums in elementary school right now. A short story real quick. So I have a daughter who's about your age. She's a sophomore in college, right? And when she was in 3rd grade, she hasn't taught this in 3rd grade, but I was teaching this here in 3rd grade when she was in 3rd grade. And she was really, really struggling with how to do multiplication in the standard multiplication way that most of us were taught. She was struggling with it. And she's not typically somebody who struggles with math, so it was sort of an odd thing to happen for her to not be getting it. And so I showed her a couple of different methods, this being one of them, and she just gravitated to it. For whatever reason, it made sense, and it's what she used for a while until she could do the other method effectively. She eventually went over and did things the other way, but this was a really good bridging point for her. So it's kind of a cool way of doing lattice multiplication. So part of the when would I use this in real life might be in helping your son or daughter when they're in about 3rd grade. You just never know, okay? All right, so we're going to take a look at how we use lattice method for finding 912 times 483. These are 3-digit numbers, right? What that means is that we're going to create a rectangular grid that is a 3 by 3 grid. Okay, so it's going to have 3 columns, 3 rows.
How big is this?
You just need space to be able to write inside the boxes. Sorry, let me move out of the way. And they're kind of approximately the same size. It's not a big deal, but it talked about splitting the boxes into diagonals. That is like this. We're going to make each box split into a diagonal. Okay, all good? All right, it doesn't matter which number we take next. We take one of the 2 numbers. One of them is going to go along the top, and one of them is going to go along the right. Okay, so I'm just going to do them in order 9, 12. So I'm going to put my 9, 12 along the top. So this is 9, 1, 2, and then 483 along the side. So 4, 8, and 3. So one of the reasons that standard multiplication can be really confusing for kids is because you're multiplying and adding in the same process. Think of what you do, right? Like you multiply, like if I were multiplying this in standard multiplication, 9, 12 times 483, I'm doing 3 times 2, and that's 6, and then I'm doing 3 times 1, and that's 3, and then I'm doing 3 times 9, and that's 27. But when I get to the 8 part, put a 0 here, 8 times 2 is 16, and I put a 6 here, and I carry a 1, and in the middle of the multiplication, I'm now adding. Are y'all tracking with me? That's confusing, all right? That's multiple steps at the same time, and that can be kind of a hard thing to process. So what this does is it doesn't have those multiple steps happening at the same time. We're going to do all the same multiplication steps, but we're going to isolate the multiplication from the addition. So again, it doesn't matter what order we go in, so I'm just going to start in the top left corner. And what we're doing is we're going to multiply the column header by the row. So it's going to be 9 times 4. Right? 9's along the top column, 4's along the top row. What's 9 times 4? 36. So 36 means I'm going to write a 3 in the top corner, a 6 in the bottom corner. And I'm going to do this for every one of my 9 boxes. And we could have done it for 2 by 2s and done 4 boxes. We could have done this for a 4 by 4 number, a 4 by 3 number. They don't have to be the same. So you can literally do this with any multiplication that you'd like. You could do it with decimals multiplication too, by the way. All right, so then I'm going to do that. I'm just going to move across my top row. I have a 1 times my 4. That's 4. And the 4 goes in the bottom corner. Okay, so single digit's going to go in the bottom corner. Double digit's going to spread across. 2 times 4 is 8. So there's an 8 right here. Next row, 9 times 8. 72. Some of you are thinking hard on that one, I could tell. 7 in the top corner, 2 in the bottom corner. It's okay. 1 times 8. 8. Here we go. And 2 times 8. 16, just like that. Okay, are we getting it? Making sense. This step's okay? All right, last row, 9 times 3. 27. 1 times 3. 3. And 2 times 3. 6. Okay, we're done with multiplication. You ready? Next step's addition. Here's what you do. We're going to extend the diagonals of each of these boxes. I'm so sorry. Do your best to squeeze it in, Aubrey. Okay, it matters where we start now. We do have to start in the bottom right-hand corner, okay? Now, the only numbers that are up for doing anything with are the numbers that are inside the box. So all of the numbers along the outside of the box, we're done with them. Don't do anything with them else, okay? We're not using them. We're only using the numbers that we've got inside the box. So this 6 right here is addition. We're doing addition, so it's just 6 because it's the only numbers. So it's pulled down here. But my next diagonal, you see I have a 6 and a 3, and I add them. So 6 plus 3 is 9. And so I write a 9 down here. So I'm adding along my diagonal, just like I would have added in the middle of the multiplication for standard multiplication. The next diagonal has a lot more in it. I have 8 plus 1, which is 9, plus 8 is 17, plus 7 is 24. Good job. All right, so we're going to write our 4 down here, and we're going to carry the 2. So the 2 does get carried to the next diagonal over, just like it would with standard addition. Now we have 2 plus 4 is 6, plus another 2 is 8, plus another 2 is going to be 10. So I'm in this column right now. Some of you are looking like, where'd she go? We're in this column. So we're adding 2, the 2 that got carried, the 4, the 2, that's 10. So I'm going to write down a 0, whoops, and carry a 1. So these are carried numbers right here, right? The 2 and the 1. Now I have 1 plus 6 is 7 plus 7 is 14. I'm going to write down a 4. I'm going to carry another 1. This is my last one. So I'm highlighting my carried ones just to draw attention. And then I have 1 plus 3 is 4. Okay, here's the deal. You have a calculator, correct? You should be able to check and make sure that you did every piece of multiplication correct and every piece of addition correct. You should be able to take your calculator and make sure that 912 really is the answer you're getting along the bottom here, right? So don't just not check. That would be silly. So somebody grab a calculator and let's make sure. what we just got is that we believe that the answer should be 440,496. 440,496. Is it? Yes, I got a thumbs up from Taryn. Yes, some nodding. Wonderful. Okay, so check the work. I'm not doubting that you know how to multiply and add, but we all make mistakes. There's a reason when I submit reimbursements for the church, because we buy stuff for the church, that I always use my phone to add them up, because I'm notorious for making a mistake with my addition. I know how to add, but I make mistakes. Okay, so just be careful, catch your mistakes.